Chapter 4 Linear Operators. Problem 4.1 Operator norm 1. Lemma 4.3. Let x, norm sub x, and y, norm sub y, be normed vector spaces, and let T be a bounded linear operator from x to y, so T is in L of x, y. We want to show three equivalent descriptions of the operator norm of T and one basic estimate. Part 1. We claim that the norm of T in L of x, y equals the following three quantities. First, the supremum of norm T x sub y taken over all x in x with norm x sub x strictly less than 1. Second, the supremum of norm T x sub y taken over all x in x with norm x sub x equal to 1. And third, the supremum over all non-zero x in x of norm T x sub y divided by norm x sub x. Part 2. We claim that for every x in x, the norm of T x sub y is less than or equal to the norm of T in L of x, y times the norm of x sub x. Part 3. Finally, we claim that the norm of T in L of x, y equals the infimum of all positive constants C such that norm T x sub y is less than or equal to C times norm x sub x for every x in x. Solution to part 1. We start from the definition of the operator norm. By definition, the norm of T in L of x, y is the supremum of norm T x sub y over all x in x with norm x sub x less than or equal to 1. We now show this chain of equalities. The first equality. The set of all x with norm x sub x strictly less than 1 is contained in the set of all x with norm x sub x less than or equal to 1. Therefore, the supremum of norm T x sub y over the open unit ball is less than or equal to the supremum over the closed unit ball. To get the reverse inequality, we use an approximation argument. Fix an arbitrary epsilon greater than 0. By the definition of the supremum over the closed unit ball, we can choose a point x0 in x with norm x0 sub x less than or equal to 1, such that the norm of T x0 sub y is within epsilon of this supremum. Now scale x0 slightly towards the boundary of the unit ball from the inside. For any real number r between 0 and 1, define xr to be r times x0. Then xr is in the open unit ball, and as r goes to 1, xr converges to x0. Because t is linear, the norm of T xr sub y equals r times the norm of T x0 sub y. As r tends to 1, the norm of T xr sub y tends to the norm of T x0 sub y, which is within epsilon of the supremum over the closed unit ball. Hence, for r sufficiently close to 1, the norm of T xr sub y is strictly greater than the supremum over the closed unit ball minus 2 epsilon. Since xr lies in the open unit ball, this shows that the supremum of norm T x sub y over the open unit ball is strictly bigger than the supremum over the closed unit ball minus 2 epsilon. Because epsilon was arbitrary, we have that the supremum of norm T x sub y over the open unit ball is at least the supremum over the closed unit ball. Thus, the first equality holds. The second equality. The unit sphere is contained in the closed unit ball, so the supremum over the unit sphere is less than or equal to the supremum over the closed unit ball, which we have already shown equals the supremum over the open unit ball. To obtain the reverse inequality, take any point z in X with norm z sub x strictly between 0 and 1. We can normalize z to lie on the unit sphere by defining u equals z divided by norm z sub x. Then u has norm 1 and z equals norm z sub x times u. By linearity of t, the norm of tz sub y equals the norm z sub x times norm tu sub y, which is strictly less than norm tu sub y, because norm z sub x is strictly less than 1. This shows that the norm of tz sub y is strictly less than the supremum of norm tx sub y over all x with norm 1. Since the case x equals 0 is trivial, we deduce that the supremum over all x with norm x sub x strictly less than 1 is less than or equal to the supremum over all x with norm x sub x equal to 1. Combining this with the earlier inequality, we conclude that the supremum of norm tx sub y over the open unit ball equals the supremum over the unit sphere. The third equality. The unit sphere is contained in the set of all non-zero x, so the supremum of norm tx sub y over all x with norm x sub x equal to 1 is less than or equal to the supremum over all non-zero x of norm tx sub y divided by norm x sub x. For the reverse inequality, take any non-zero vector z in X and again normalize it by setting u equals z divided by norm z sub x. Then u has norm 1. Because t is linear, the norm of tz sub y divided by norm z sub x equals the norm of tu sub y. Hence, the quotient norm tz sub y divided by norm z sub x is bounded above by the supremum of norm tx sub y over all x with norm 1. Taking the supremum over all non-zero z, we get that the supremum over all non-zero x of norm tx sub y divided by norm x sub x is less than or equal to the supremum of norm tx sub y over the unit sphere. Combining the two inequalities, we obtain equality of these two quantities. Putting everything together, we have shown that all four expressions in part 1 are equal. This completes the solution to problem 4.1, part 1.